What is a lab session about? Lab session is frequency domain analysis, and as I mean, right away, it may look like, I mean, what does this really mean? That's actually what we're going to try to tell you. And then they're very, very interesting lab tasks that we have designed for you. We're very much related to what some practical applications are in the engineering domain. Okay. And so before I begin with what really frequency domain analysis, let's me begin with some problems here, okay? And that's what we're going to try to do. As a top-down approach, in the sense that let's try to give you some problems which you can come across, you will come across in engineering applications, and let's just see, okay, how we're going to be able to solve them. So this is the first problem, which is that of noise removal. So once again, I have that dreaded, maybe by now, voice of my own. So let's hear that.
प्यारे बच्चों, मेरी आवाज सुनो और सुनते चले जाओ.
Right. So it's the same Meri Awaz signal, except that that signal has now been corrupted with an interference, right? And that interference is actually something I got from the internet. So that's actually dog whinings. And who can tell me, if you were to separate the dog whinings out from my own voice, I mean, what's the differentiative factor between the two? Can somebody uh, point this out? Motsim, can you? Okay, very nice. So there's a pitch. So that's one of the common answers that we're getting on the chat window. That's a pitch. So my voice appears to have a lower pitch, and the dog whinings appear to have a higher pitch than my own voice. Okay, so that's a key observation. They appear to be of different pitches, right? So maybe perhaps there's something that we can do with regards to these pitches to be able to separate them out, as we're going to see in this lab task. So this is exactly one of the lab tasks that you're going to be doing at the end. Okay. Now let's talk about another problem. And this problem, by the way, is one of the S project or the senior year design projects that we did, that one of our groups did in electrical engineering a year ago, I think, or maybe a couple of years ago, which is contactless measurement of vital signs. So your breathing rate using Wi-Fi signals. And this should excite you. Why? Because Wi-Fi signals, as you know, are primarily meant for communication applications. You're sending data over the air in a wireless fashion, and that's what Wi-Fi really does. But over the years, in recent literature as well, researchers have been using them for sensing applications. And this is one example sensing application that we use it for. So this student that you see here is one of our alumni. He's now an alumni, so he's at Rutgers now. And you have a phone transmitter here. So this is a Wi-Fi transmitter, and you have a phone receiver here. And that person is sitting in the middle, and all this transmitter is doing is sending data to this phone. And what happens is, as the person breathes, as Kaiser breathes, so his name is Kaiser. So as Kaiser breathes, that changes the signal strength, the strength of the received signal with the movement of the chest. And what you observe at the receiver, so this is an actual observation that we made this is an experiment that these guys did, the students did with their phones. So you have an app on the phone that can capture the signal strength, okay? And you observe that the signal strength goes up and down, and this is actually reflective of how your chest moves. So the chest moving in and moving out changes the received signal strength, and which is called the received signal strength index, RSSI, okay? And again, our objective is going to be to do what? Given this signal, I wish to extract the breathing rate of that person. Okay. Any ideas how we can do that? I mean, regardless of whether you know frequency domain analysis or not, kya karenge so to be able to extract the breathing rate measurement? Any ideas? Irtaza?
So, considering breathing would be something which would have the lowest amount of frequency from
Yeah.
all the other signals which you would observe in
Yeah.
from the Wi-Fi signal, maybe you could figure out some way to separate the lowest possible frequency and obtain a measurement of that in some way or another.
Excellent. Excellent. Zabardast. So that means, what you've hit the nail at exactly the right spot. So it has to do something with frequency. You need to separate some frequencies out and do some sort of frequency analysis, right? So that's what where we're headed. Now, why would you have this kind of an application? I mean, you can say, okay, yaar, I mean, yes, this is a fancy measurement kind of a thing that you're doing, but it has very, very practical applications. So, for example, in the context of, if you recall the first problem that we talked about in the very beginning, lab one में, कि COVID-19 hai, you have to have people at home who need to be monitored whether their vital signs are going off the charts. And one of the ways of monitoring their respiratory rate or respiratory vital signs is through this contact-less measurement. You don't really want sensors to be placed on their chest and wires coming out and going into another receiver somewhere. I mean, that affects the person's mobility. So it would be really, really nice if you just have a Wi-Fi transmitter at your home and you're moving around, and that Wi-Fi transmitter, on top of letting you hear what I have to say, would also let you measure how far or how fast you're breathing, or how, and some people have done this, what is your heartbeat, okay? So that would be really, really an interesting application. And there's some, it's not really ahead of its time. There are some commercial, and maybe I'd point you to some of these as well. There's some startups that are trying to work on these kind of ideas, okay? And this was one of the SPOD that we did a year ago or a couple of years ago. Now, related to this is another SPOD, which we're actually doing right now, and one of the TAs is a part of that issue here. So Isha is part of this SPOD, where we're trying to measure the breathing rate once again using an RFID tag. Okay, so RFID tag, anybody is familiar with what an RFID tag is? Anyone? So how many of you have went on the motorway or on ring road, Lahore ring road में E tag इस्तेमाल किया कभी किसी ने, or M tag or easy tag, or even your smart cards at LUMS, right? I'm not sure if the freshmen were issued the smart cards yet, but your smart card, for example, have something called an RFID tag. It's a radio frequency identification tag, right? And what this does is, if you bring this in the vicinity of a reader, it just does not have a battery and is energized by a reader, and it transmits at some identification sequence, right? So that you know that this person is Momin. Okay? This card belongs to Momin. Or if you are going on a motorway and you pass through that reader, so that person knows that the reader knows, or the system knows that आपके account में कितना balance है अभी, and you have to deduct 45 rupees or if you're traveling on the ring road, right? And all of that is done through this something called an RFID tag. And we're trying to use it, as some researchers have done in the recent past, to measure the breathing rate once again, which is you place this on your chest, and as your chest moves, the signal varies, the reflection, the properties of the reflection varies, and in particular, the phase of the reflection varies. And maybe you can, if I can show you a plot, this is what the phase looks like. And this is actually an experiment that Isha did. So this is at her home. So we transported the RFID reader to her home so they could do the experiments there. And she's done this herself. And this is a measurement of a phase as a function of time. And in there, as Irtiza mentioned as well, is embedded somewhere or some hidden somewhere the breathing rate of the subject. Okay. And our job is to try to extract what the breathing rate was. And maybe embedded in there is the heartbeat as well. And that's much, much more harder to extract, but that's something we're trying to work on. Okay. And the key idea, once again, is that you have to do some sort of frequency domain analysis here to be able to extract what the breathing rate of this person is. Okay. Similar idea. So this is another project that we worked on last year, which is once again using Wi-Fi to monitor a machine, a generator, if you will, or a motor, if you will. And once again, with those changes in RSSI, we're trying to measure the machine ki RPM kya hai, what is the revolutions per minute of this machine in a contactless fashion. So there's no contact, there's no sensor attached to the machine per se, but rather you're just using radio waves to try to determine what the revolutions per minute is. And this is exactly the same sort of frequency analysis where we would have to apply over here as well. And the list goes on and on. And so the other other examples, interesting exploits that we do, which are not necessarily related to machines or frequency domain analysis. So this is once again from 3 years ago, and um, so this is where we use Wi-Fi to monitor के कमरे में कौन सी equipment on है. So is the pedestal fan on? Is the microwave oven on? Is the washing machine on? Is the ceiling fan on or not? And moreover, trying to measure kitchen speed se on and so on and so forth, just using Wi-Fi signals. This again is another project which is once again using Wi-Fi to try to detect कि आप गाड़ी में कहीं चलाते हुए गाड़ी को फोन तो नहीं यूज कर रहे. And if you have phones on your, so it has Wi-Fi signals, it can actually detect whether you're yawning. So we were able to detect a person there. Is he feeling sleepy? Is he using a smartphone? Is he moving his head a lot? And all of that we were able to detect with Wi-Fi. So this is just slightly off the track, but trying to give you some advertisements, if you will, so with the kind of projects that we've done from our undergraduate research. So this has all been published, by the way, with our undergraduate research. Okay. Now, the conclusion that we have here is that there's a potential tool to solve all of these practical problems that I've shown you, I've given you, is something to do with frequency. We have to have some analysis of frequency domain. Okay. And this is the topic, this is the subject of this particular lab, which is lab 4. Okay. So let me just start out with a simple sinusoid, right? So this is a sinusoid that we've dealt with in lab 3 as well. And sample musical notes are actually tones. So note D, for example, is 294 kilohertz. Note A is 440 kilohertz. And of course, and something you will all be familiar with already. This is note D. This is note D. And this is note A, which has a higher frequency. So we know that the higher frequency somehow has an associated with it a higher pitch, right? And that's something we've tried out already with in lab number 3, right? So in this sinusoid, as the frequency goes up, the pitch goes up as well, which is audible to you, which you can perceive as well, right? Now, if you try to generalize this idea to some speech, right? If I play my own sound, and maybe this is a sound that you're familiar with.
EE100 is awesome.
So this is my daughter. This is my 6-year daughter who had this hidden message embedded inside one of the one of the lab 3 tasks, and this is her voice once again.
EE100 is awesome.
Right, and my speech.
EE100 is awesome.
I'm speaking the same sentence, right? So this is the same sentence, yet the two tones or the speech appear to be very, very different. And of course, you would immediately say, yeah, that difference there is in the pitch, right? So pitch is something that perhaps we're all familiar with. But we earlier saw in the sinusoids that the higher the frequency, higher the pitch. So the pitch has to do something with the frequency, right? But how do you define the frequency of a speech signal, which is seemingly so complicated, so sophisticated, right? So there has to be some relationship of frequencies with the speech signal, and that's what we're trying to figure out, right? So how does the higher pitch correspond to higher frequency? What does frequency really mean as far as some speech signal is concerned, right? So in order to answer this, let's see that if you have a sinusoid available, right? So if I give you a single sinusoid, a single tone, and you have this waveform available to you, and I ask you to look at this waveform and try to determine what the amplitude is, what the frequency is, what the phase is. क्या करेंगे? How would you measure these 3 unknown parameters? So, Abdur Rahman, how do you measure these parameters? Abdur Rahman, can you hear me? Okay, so Isha Imran, can you unmute yourself?
Yes, sir.
Yeah, so how if I gave you this curve and I ask you to determine what the frequency of this curve is, determine what the phase of this curve is, and determine what the amplitude of this curve is. क्या करेंगे? What do you do?
Not sure.
So if I give you, okay, Hania, go ahead.
So for frequency, we would find the period of the graph and
Good.
then do 1 over time to find the frequency.
Excellent.
For amplitude, we would find the distance from the rest position.
Yes. Excellent.
And yeah.
And once you have both of those, your phase you can evaluate by just picking any point and see what the phase is. So you just have to solve some equations, right? So the bottom line is there's some underlying mathematical phenomena that you would have to solve, right? To get the unknown parameters A, F, and theta from this time domain curve. Okay, so that's the underlying principle where you can go from a time domain sinusoid to its parameters, which are the amplitude, frequency, and phase. Okay. What about two tones? If I mix these two tones up, right? So I've now this is a relatively more sophisticated tone, and which is actually a mixture of two tones, right? And if I play this out, right? So it's a mixture of sinusoids now. It's no longer a single sinusoid. It's a mixture of two sinusoids, where each one of those two sinusoids has a certain amplitude. Each one of those two sinusoids has a certain frequency and certain phases, right? So there's a typo here. So this should be A2, this is F2, and this is theta 2. Okay. Now, if I give you this time domain signal, can you determine this A1, F1, theta 1, A2, F2, and theta 2? And the answer to this, once again, is yes, because you're given so much information as far as the time domain signal is concerned. You just have to solve some equations. It's just a matter of solving some simultaneous equations to give you these 6 unknowns, right? So there is, so the question is, given this mixture of tones, can we unmix the two tones together? In other words, can we determine the amplitudes, frequencies, and phases of the two sinusoids? And the answer is yes, using some mathematical analysis, okay? And this by itself should be really, really sort of exciting here, because what you're saying is that if I mix up two sinusoids together, मैंने उनको mix कर दिया, right? There is a way of unmixing them. Typically, that's not what you can do in real life, right? दो चीजें आप mix कर दें, you will not be able to unmix them because there are many combinations that could result in that mixture, right? But in certain cases, that's not so. For example, primary colors, if you mix two primary colors up in a very specific proportion, that's going to give you a very unique color, right? So given that unique color, you will be able to determine what the individual proportions of those colors were. Just like this, using this some mathematical analysis, which turns out is some Fourier analysis, we can unmix these tones, right? So that's some beauty to it. There's some excitement to it, right? There's some tools that would allow you to do that. And this is a representation, which we're going to say this is the frequency domain representation of those mixture of two sinusoids. So you have an amplitude representation and you have a phase representation. So on the x-axis, I have frequency. On the y-axis here, I have the amplitude, right? So for that particular example that I showed you, this was actually a mixture of two sinusoids, which had frequencies of 440 kilohertz, 440 hertz, and 294 hertz. And the 294 hertz sinusoid had an amplitude of 0.2, and the 440 hertz and an amplitude of 0.5. So this representation, which is a graphical or a visual representation, illustrates what the amplitudes were as a function of frequency. And all of the amplitudes for other frequencies are all 0. Okay? So this is a very nice visual representation or a functional representation of what the frequency components in that mixture of tones was, right? At the same time, the phases are extremely important as well, right? So these phases are the phases in radians as a function of the frequencies. At 294 hertz, the phase was 0.7854 radians, and which is pi by 4. And at a frequency of 440 hertz, the phase was 1.57 radians, right? And these two curves together specify these frequency domain representation of that time domain signal, of mixture of tones. Now the question is, what about some more complicated mixture of sinusoids? So this here is a tone, is a mixture of tones. But these mixture of tones is more sophisticated in the sense that I actually made up this on my own. I've added up 4 sinusoids here. And the question once again is, will you be able to separate them out? It turns out, yes, you will be able to separate them out. Once again, some mathematical analysis, which we're for now considering as a black box. कोई एक mathematical machine है which can separate these sinusoids out into their individual amplitudes, frequencies, and phases. Right? So for this particular example, it turned out when I apply this mathematical analysis or as this tool set, this is the breakup that I get. So what's important for us to understand is not exactly what that mathematical analysis is, because that's perhaps beyond the scope of the inner workings of that analysis, is beyond the scope of a freshman course, right? However, what's important for us to understand is this representation, right? This representation. And this representation is what? This representation tells you that this signal that I showed you earlier, this complicated looking signal, can be actually broken down into 4 sinusoids, right? And these sinusoids have frequencies of 294 hertz, 440 hertz, 780 hertz, and 900 hertz. And not only that, this analysis also yields to me, yeah, 294 hertz ka amplitude kya tha, 440 hertz का amplitude क्या था, 780 का amplitude क्या था, 900 hertz का amplitude क्या था, and also gives me information about what the phases were for each one of those individual, 4 of those individual frequencies as well. So I have a function of frequency, which is the amplitude, which tells me what the amplitudes were as far as the constituent signals were concerned, and the function of frequency, which tells me what the 4 phases were as a function of frequency. Okay. So this is an unmixing of frequency tones, right? And this is the frequency domain representation of the example that I saw you earlier, right? So there's an amplitude representation and there's a phase representation. Can you think of some mathematical tool that you would have come across in your high school and your matriculation or your O levels and A levels, which can combine these amplitude and phase together into one compact representation? Right? Can you think of a number which has a phase and which has an amplitude as well? What is that number? Can I combine the amplitude and the phase into one compact representation of a number? Anyone? I mean, feel free to type it up if you're shy to unmute yourself, which you should not be. All right, excellent, Salman. Salman, can you unmute yourself and explain to me what e raised to power I pi actually means?
So, sir, basically, if you have a sine or cos function, you can basically represent it in this form as well, where any variable before e is the amplitude, and to the power I pi gives you the angle.
All right. So, what is a number called? I mean, there's a specific name for
Euler's constant.
Euler's constant, exactly. There's a certain name for that I'm looking for. There's a certain terminology that I'm looking for, which is synonymous with complicated or sophisticated
complex numbers.
Complex numbers. Excellent. Okay. So complex numbers are complex not because they're difficult. Complex numbers are complex because that's their name. Okay. So that's how I look at it. Right. And that's one of the reasons, as you were seeing the handout as well, I have a note there that we engineers do not like to use the adjective complex for describing stuff. I will not describe EE100 as or a certain EE100 lab task as being complex. I may define it as being difficult, but not as complex. Okay, because complex has a very, very different interpretation or different implication in engineering circles. Okay. So we're looking for a complex number here, and that nice compact representation, which gives you the amplitude as well as the phase, is something called a complex number, which is not necessarily further math. Further maths make sort complex numbers nahi hote. Complex numbers is a fundamental math problem which is not further math. Okay, so we're looking for a complex representation, right? And a nice way I can combine these two, amplitude and phase, together into one compact representation is through a complex representation. Okay, it's a complex representation. So in other words, I can say this is 0.1 has a complex number which has an amplitude of 0.1 and a phase of pi by 2, right? And you combine this together into this functional form. So at f equals 294, which is 294 hertz, the signal has an amplitude of 0.1 and a phase of pi by 2. And this is a nice, very, very nice single line representation of what the phase is and what the amplitude is. For 294 hertz, for 440 hertz, the amplitude is 0.5, the phase is pi by 4. 780 hertz में amplitude 0.3 और phase क्या है? Phase 0.
Or any multiple of 2 pi, because
excellent.
0 and 2 pi, any integer increment of 2 pi would be the same.
Excellent. So you have the right answer. Basit has the right answer as well. Omar Malik, you have the right answer as well. So this is 0, right? So 0 is the same as 2 pi. 0 is the same as 360 degrees. The phase goes around in circles. Okay. And so at 900 hertz, the amplitude is 0.1 and the phase is pi radians, which is actually 180 degrees. Okay. And it's okay if you don't remember it then, Hania, that's fine. All you need to know is this is a complex representation as far as we're concerned as for EE100, but you may need this for your other maths courses. But as far as EE100 is concerned, you have a certain number which has a certain phase and a certain magnitude, and MATLAB is going to allow you to compute that magnitude and the phase through certain commands. Okay, and the magnitude represents the amplitude of the sinusoid, and the phase of the complex number represents the phase of that sinusoid. Okay, so this is a nice compact representation that we're going to be dealing with, and which your MATLAB command is going to give you as well. Okay, so we're ready to summarize here. So there's the frequency domain representation works as follows. Irta, you have a question? Go ahead, please.
Yeah, I have a question.
Yes.
So when we're representing it in the form of a complex number, we don't use the complex component, right? Because we're not interested in it per se.
So complex.
So we don't actually
you're talking
need
about the
sign
imaginary
component,
right?
Yeah, we don't need the imaginary component. Sorry, we don't need the imaginary component when you're representing it in the form of a complex number.
Okay, so it's a complex number has a real part and an imaginary part, both of them together. Both of them together make the complex number, and there's a polar representation and there's a rectangular representation. If you remember that, okay? So we don't want to go into a lot of those details here because that's not where objective is. Okay, and so I can come up with an equivalent polar rectangular coordinate representation for this as well, right? Which would of course have an imaginary part as well. Okay? Right? And when you do it in MATLAB, आपको imaginary part nazar आएगा, right? And we can explain that later as well. Okay? So here's the summary here. So you have the time, something called the time domain, and you have something called the frequency domain, right? So time domain is a signal that the sinusoid that we saw, right? Any mixture of sinusoids, which is x of t, which is the time domain signal, we'd say that's a time domain signal. Okay, and then there's a frequency domain representation of that, which is of this form, which just tells you, yeah, what is this signal made up of? We say that this signal is made up of sinusoids, right? And it's actually made up of 4 sinusoids, as you can see here. The first sinusoid has a frequency of 294 hertz, then the 440 hertz, 780 hertz, 900 hertz, with corresponding amplitudes and with corresponding phases, right? So we say that this is the frequency domain representation of this time domain signal, and they're interchangeable. Okay, and once again, essentially what you're saying is roughly in generalized form is a sum of sinusoids of different frequencies, right? When they're mixed together, you can separate them out. You can unmix them out into their corresponding component frequencies, their amplitudes and their phases. And that representation, I'm going to call this as x of f. And at the time domain, I'm going to call this as x of t. Basit, do you have a question? Go ahead.
Yes, sir. Sir, सर इन ए लेवल वी वर टॉट कि हम सिर्फ उन वेव्स को आपस में सुपर इम्पोज कर सकते थे, मिक्स कर सकते थे जिनकी फ्रीक्वेंसी सेम होती थी, इंटरफेरेंस तब होती है. सर हाउ कैन वी आई मीन मिक्स दीज waves together when they don't
Okay.
even have the same
So
frequency?
there's no way for you to unmix those. Okay, so that's an excellent point. If I understand your question correctly, you're saying that if I mix two sinusoids up which are of the same frequencies, is that what you're saying, right?
Yes, sir. And plus, how can we mix these different waves with different
Okay,
frequencies
so you can
together?
mix them up, but there's no way for you to unmix them. Okay, there's nothing you can do there. I mean, kuch limitations are that we as scientists and we as engineers need to understand. And that limitation is if you mix up two sinusoids which have the same frequency, there is no way for you to be able to unmix them. Think about that for a while, why that is so. Okay? But that's an excellent point. And others can think about this. And we can put this up in the discussion forum. Okay, TS? All right. So here's the point. So if you have sinusoids of different frequencies, right, you can unmix them, and when you unmix them, that's called Fourier analysis, right? And this is thanks to somebody called Joseph Fourier. Can you guess ये काम उसने कब किया था? Right, this result is a very fundamental result. That's a
1800s or 1900s.
1930s, that's where this result was derived. So this is more than about a century ago, right? So a little less than a century ago, when all of this theory was developed, where Fourier said a mixture of sinusoids can be broken up into their components. Okay? And that's called Fourier analysis, where the process of where you unmix those sinusoids, that's called Fourier analysis, or the process of unmixing is called Fourier analysis. And the process of mixing them together, that's a much easier process to do, right? So that's mixing, that's Fourier synthesis. So everything was not done in the 1920s. Uske baad bahut kuch hua hai, and maybe we can talk about that sometime later. So the process of mixing them together is something called Fourier synthesis. So this is a fundamental result with sinusoids. You mix sinusoids of different frequencies up, you can unmix them. There's a guarantee that you're going to be able to unmix them. And of course, if there's unmixed version, you can mix them together, and that's called Fourier synthesis. Unmixing is called Fourier analysis. Okay. Now, here's an important question. We've been talking about sinusoid, right? So sinusoid. But how is this sinusoids important? What practical implication does it have, right? Are real world signals, aren't they more sophisticated than a sum of sinusoids? You see, I've not used complex here. I mean, I could have used complex here, more complex than sum of sinusoids. That would have meant an entirely different thing as far as me as an engineer is concerned, right? As if I'm an engineer, I'm going to say more sophisticated than a sum of sinusoids, right? And this is an important question. And the very exciting answer to this is that's not really true. And Fourier's contribution here was, and all of those people, other people involved as well in developing this theory, says that all real world signals which are of practical interest, and speech is one of those, they can actually be broken down into sum of sinusoids, right? In other words, you can, all practical signals of interest have sinusoids as a fundamental building block, right? Just like you have primary colors, you can use those primary colors to make up any color in the universe. Sinusoids are primary signals, if you will, and they're called the basis signals, right? Using which you can build any signal of practical interest which exists out there in the universe, right? And this is really awesome. I mean, this really excites me कि यार वाकई इतना जबरदस्त रिजल्ट ड्राइव कर लिया उन्होंने, वो भी 100 साल पहले मुझसे, जो कि मुझे अभी तक नहीं समझ आता सही तरह, right? So this is really awesome. Okay, what are the practical implications for this? So here's the frequency domain representation of speech. Okay, so over here is a speech signal, right? And this is actually, I believe, my speech.
EE100 is awesome.
So this is Hania, right? This is my daughter, 6-year-old daughter, as her speech, which I have broken down into a sum of sinusoids through something called the Fourier transform, or something called the Fourier domain representation, using a MATLAB function that we're going to provide to you, right? That we're going to provide to you. Primary colors को 0 0 0 कर दें तो वो Aisha, that makes up white. Okay, 1 1 1 सारी कर दें तो फिर that makes up black, right? Or you can argue कि आप White is an absence of any color. Well, but that's besides the point. Okay, so this is the frequency domain representation of this time domain signal, which is speech, right? So what I'm once again saying is that this speech signal can be broken down into, once again, a sum of sinusoids, and that sinusoidal representation or frequency domain representation is this red signal here, which let's say is कि यार 0 hertz पे इतनी amplitude होगा, इस पे इतना होगा, इस पे इतना होगा, इस पे इतना होगा, इस पे इतना होगा, and so on and so forth. For all of these values ranging from 0 to, in this case, 2.5 kilohertz, right? Actually 25 kilohertz. Okay. Now, this is the time domain, this is the frequency domain. Let's go back to the earlier example or the question that I posed. What is the relationship between speech's pitch and frequency? As we said, कि higher frequency का मतलब higher pitch होता है in single tones, but what does it mean for a sophisticated signal or for a complicated signal such as speech? This is what it means. So this is Hanya's
EE100 is awesome.
Fourier decomposition. This is the Fourier series representation, and this is my Fourier series representation.
EE100 is awesome.
Right? So the blue curve or the blue thing that you see is a Fourier representation for my voice. This red thing that you see is a Fourier representation for Hanya's voice. Right? What is the difference that you observe? Who's going to tell me? Qasim, what difference do you observe?
Sir, the amplitude of your daughter's voice is much separate from our voice, which means more frequency and more pitch. It's a high pitched voice.
Good, right? So, and there are many other correct answers in the chat box as well. That's excellent. So the range of frequencies is different. Thank you, Mukim, for putting words in my mouth. So the range of frequencies is different in Hanya's speech as compared to my speech. And how is that different? Hanya's speech has a concentration of components, relatively higher concentration of components in the high frequency range. So somewhere over here, okay, as opposed to mine. Maybe somewhere over here is smaller, around 0.5 kilohertz, 5,000 kilohertz around. So my the frequency decomposition of my speech is smaller compared to Hanya's, and that means that using this Fourier decomposition, we've been able to quantify somehow what the relationship between pitch and frequencies is, exact, precise description of how frequencies affects speech. Okay? So that initial observation that we made with a single tone is now can be generalized to this sum of sinusoids or more complicated or sophisticated signals such as that of speech, right? So this gives us a very nice visualization of how my speech is different from my daughter's. Okay. All right. So what are some of the applications that you can use this for? Here are some. Okay. So this is once again time domain signal जो हमने original बात की थी.
प्यारे बच्चों, मेरी आवाज सुनो और सुनते चले जाओ.
My objective is to remove, and your objective is going to be to do the same in the lab task, is to remove that dog whining, right? वो निकालनी है. How do I remove that? Now, can somebody try to engineer a solution for this? Now that you're familiar with Fourier transform, Fourier representation, consider the fact that you have a black box available. ठीक है, एक black box है जो उसकी Fourier decomposition को मैं उसको break up कर देता है. ठीक है? Can you think of a solution, Vaji?
Yes, sir. So basically, what I would do is कि जो शुरू में हमें आवाज आती है ना, like जो शुरू में हमें छोटी आवाज आती है, तो उसको एक तरह से उसकी फ्रीक्वेंसी हम कैच कर लें और उस फ्रीक्वेंसी को हम पुट कर दें उसके अंदर जो फोरियर बॉक्स है और वो उसको उस स्पेसिफिक फ्रीक्वेंसी को रिमूव कर दें पूरी वॉइस में.
Excellent. फ्रीक्वेंसी को रिमूव करने का मतलब क्या है? You just null it out.
कि उसको सेपरेट कर देना, मतलब कि फोरियर जो उस फॉर्मूले से सेपरेट कर देना बेसिकली उनको.
Zabardast. That's excellent. That's correct. Anybody else have any other ideas? Ahmed, Shumail, any ideas? I mean, so if your name is listed, so all of your names listed alphabetically here, by the way. So your bad luck if your name starts with an A. That's what I can on my screen.
The frequency, the frequency which is noisy frequency, uski frequency higher hai, So the higher frequencies can be cut out compared to yours.
Excellent, right? So that's exactly what we're going to do. And this is called filtering. This is frequency selective filtering, which is an extremely powerful tool to get rid of unknown interferences as long as Basit suggested, as long as there's a clear separation in the frequency ranges. ठीक है? अगर वो नहीं है, तो this is not applicable. You may have to do something else. Okay? So here's what we're going to do. We're going to take the Fourier transform, right? And this figure in front of you actually represents what the Fourier transform of this noisy time domain signal, uska Fourier transform kya hai. Now, from my previous figure, Fourier transform and Fourier analysis, Hussein, I'm going to use them interchangeably. Okay? And as this I say in the handout as well, okay, I'm going to use different terms to mean the same thing. I may use Fourier transform, may use Fourier analysis. I may use the word spectrum as well. Okay, spectrum representation, right? Spectrum, all of you should be familiar with. Spectrum, Pink Floyd, I see Hussein logo, DP hai, that has a spectrum in there, right? So spectrum is something to do with frequency, something to do with wavelengths, and that's why we also call it a spectral representation. Okay, so from my previous, so over here, I know this was my uncorrupted noise, and you can see that this was centered around 0.5, 0.5 kilohertz se pehle tha almost, okay? Or actually, I would rather say it's 4 kilohertz se niche tha. This would maybe just noise, right? So I know from the previous analysis that my own voice is centered around, is the maximum frequency for that is around 4 kilohertz. And from that, I can conclude that everything that appears after this 4 kilohertz from here to here, perhaps is that dog whining. And let me try to separate out therefore, right? So what I do next is I apply this masking operation or a filtering operation here, in which what I would want to do is I would want to keep these frequencies as they are and the frequencies above 4 kilohertz as being nulled out. And I'm going to do this operation myself, and you're going to do this operation yourself in one of the lab assignments as well. Okay. And if I do that, so this is something called a low pass filter. And why is it called a low pass filter? Rafe, why is it called a low pass filter? Why do you think it's called a low pass filter? Rafe Khan.
It doesn't allow frequencies above a certain limit to pass, like a lower frequency.
Okay, so Rafe, I'm sorry, I was not able to hear you properly, but I'm sure you were saying it. Your answer was correct, and there are correct answers in the chat box as well. And let me, yeah, कौन बोल रहा है?
Sir,
go ahead.
Basically, a low pass filter is something that allows the frequencies which are lower than this red line. Right? Okay. The frequencies which are like above it, it basically activates that.
Right. Excellent. And so if I will take the liberty of quoting Adil Haider here, he has so you can put words in my mouth once again. So he says it only allows lower frequencies to pass, and that's why it's called a low pass filter, because it only allows the low frequencies to pass and it blocks out the high frequency components. And conversely, इसका मतलब high pass filter क्या होगा? High pass filter is a filter which would allow the high frequencies to pass and the low frequencies to be cut out. And that's one of the things that I do in the tutorial task, as you will see. Okay, so let's try to see what happens. So this is the overall process. आपने उसको Fourier transform लिया, ठीक है? I do that, Abdurrahman, don't worry. So आपने उसको Fourier transform लिया, and then you apply a masking operation, where you null frequencies out and you let certain frequencies through, and then this is called filtering, and this is the result that you get. You see, everything above 4 kilohertz, I have manually zeroed them out, okay? And I then take the inverse Fourier transform, right? So that's important, because if I have to play the audio signal again, I have to go back in the time domain. So I have to go back in the time domain, which is my speech, and this is what this sound looks like now.
प्यारे बच्चों, मेरी आवाज़ सुनो और सुनते चले जाओ.
Right, so let me play the original sound.
प्यारे बच्चों, मेरी आवाज सुनो और सुनते चले जाओ.
And this is the filtered noise.
प्यारे बच्चों, मेरी आवाज सुनो और सुनते चले जाओ.
Right, so you may be able to observe, that the noise or the interference has gone down, right? But as Shazir says, it is not down completely. I mean, you can still hear it, right? Why do you think that is? Shazir, maybe perhaps you can try to answer. Am I saying your name right, Shazir or Shazir?
Sir, it's Shazir. Am I audible?
Yes, you are.
सर इसमें दरअसल आपकी जो डॉग की फ्रीक्वेंसीज हैं वो आपकी फ्रीक्वेंसीज के साथ ओवरलैप करी हैं. सो आपने जिस तरह सेपरेशन का कोई रूल नहीं बनाया तो वो जो फ्रीक्वेंसीज उस रेंज में है 4 के अंडर वो भी इसमें आ रही हैं. तो इस वजह से हम 100% फिल्टर नहीं कर पा रहे हैं.
Excellent. So I wish we could have had some clapping here, which emotions or emoticons Zoom में allow करते हैं हम. लेकिन yeah, that's exactly. So I would want this to people to do this. So that's exactly the right answer, which is कि जो dog whining है उसकी कुछ ना कुछ frequencies मेरी voice के साथ overlap करती हैं. That might be one of the reasons, but there's another possible reason as well, which is I could try to bring this 4 kilohertz down even further. हो सकता है मेरी voice 4 kilohertz तक कहीं ना पहुंचती हो सकता है और 3 kilohertz पे खत्म हो जाती हो, right? So you can try to play around with this, right? You can try to play around with this, try to see what trade-offs exist, and I think that's one of the things that we would want you to answer in the lab task as well. Okay, so this is an application of filtering, which is called frequency domain filtering. Okay, here's an application of frequency shifting, which is I have my voice is relatively coarser, right? It has a duller tone compared to, for example, Hania's. और मैं चाहता हूँ कि यार I want to introduce some frequency effect or sound effects, and I want to take it up a notch in the frequency domain. यानी उसकी pitch मैं ज़्यादा करना चाहता हूँ. What do you think I should do? So that's another application. This is called frequency shifting. Okay. Any ideas here, Daniel?
I'm sorry, can you repeat the question?
The question is, I want to increase the pitch of my voice, right? My voice is duller, right? But I would want कि यार वो हानिया के करीब थोड़ी सी उसकी pitch चली जाए, right? So that's a sound effect. How should I introduce a sound effect?
Maybe submerge another sound with it, of a higher
If
frequency.
I submerge another sound with it, तो वो जो मेरी voice है ना वो कुछ और बन जाएगी. वो मेरी voice audible नहीं रहेगी most likely. ठीक है? Yes. So multiplying by a constant factor. Okay, Abdul Rahman, if I multiply everything by a constant, what do you expect to happen? And you can actually try it out when you're playing sound. If you multiply with something, so that it just increases or decreases your sound volume. Okay, that increases the amplitude, the greater amplitude. Excellent, Daniel. Okay, वो सिर्फ volume ऊपर नीचे करेगा. मुझे volume नहीं चाहिए. मुझे pitch improve करनी है. And I could see answers to this by, let's say, let me name a name. Ahmed Lukman, so just displace the waveform to the right by a certain interval of frequency. Excellent, Ahmed. You don't have to have a question mark there. Maybe an exclamation mark would have been more appropriate. That's the perfect answer. You just have to shift this in the frequency domain to the right, and that's like that delay exercise that we did in the last lab task, right? So that's one of the other things. If you're done that, so this should probably be easier in the sense of how do you introduce shiftings. So in MATLAB, and that's what we're going to do here. And what I've done here as a shift, I've introduced a shift of 500 hertz, right? You see, जो पहले यहाँ पे थी peak, अब वो यहाँ पे आ रही है, which is relatively higher, right? So all of this in the frequency domain is zeros. So all I've done is I've increased the frequency by a constant amount by a displacement of 500 hertz. and then I take the inverse Fourier transform. And this is what the inverse Fourier transform looks, or the time domain signal sounds like.
EE100 is awesome.
Right, and you see, I mean, this is distorted. Yes, I agree, this is distorted, but the pitch is higher, right? Because it has gone up. This was the original.
EE100 is awesome.
Right, so that was the original voice. And by the way, my voice is typically नीचे से रहती है. वो मैं हानिया की आवाज से अपनी आवाज मिलाने के लिए थोड़ा सा I had to subconsciously maybe increase my pitch. Otherwise, typically speaking, my voice is even duller than what you're hearing right now as well, by the way. Okay, so this is filtered out.
EE100 is awesome.
Okay, and there's an excellent question by Aisha. Why is it distorted? I don't have the answer right now. Maybe this is something we can try to explore altogether. Okay, so yes, this is Wally. Wally is perhaps better or relevant to today's age than ET. Jazlan, ET is a thing of the past, way too past. I'm not sure if everyone is going to be familiar with ET here. Okay, so जब मैं बिल्कुल छोटा था, that's when ET that came out. All right, so this is the application in the frequency estimation. This is another application, and this is once again data that Isha has actually measured of the equipment that we're using RFID tags. And this is the time domain signal that you get. Uske frequency domain mein gayi, and then you observe that the frequency, there's a frequency peak at 0.2136 hertz, right? And this, as somebody said in the beginning, I forget who said this, said there are going to be some different frequencies here, and you try to analyze कि वो फलां वाली frequency की क्या magnitude है, किसका magnitude ज़्यादा है, किसका magnitude कम है, and try to filter out somehow. And we see that this is the dominant peak as far as the free sinusoid is concerned. And that means it was actually a sinusoid corrupted by a lot of other things, right? And we're trying to extract the breathing sinusoid, the signal that would have resulted because of the breathing, and which was a sinusoid, and we see that's a 2.2136 hertz signal. How does that correspond to in breaths per minute? Can somebody quickly answer me? Agar frequency hai 0.2136 hertz. So what is this equivalent to in breaths per minute? I mean, you can type it up, you can unmute yourself. Anybody? Agar hertz में frequency 0.2136 है, तो per minute कितनी होगी? Aisha, why 5? Right, if the number of cycles you
12.8.
No, so you're perhaps not understanding what I'm trying to say. I'm saying if the number of breaths per second is 0.2136, what is the number of breaths per minute? Here you multiply with 60. Okay, so that's not 281 breaths per minute that you बंदा गुजर चुका होगा तब तक, और या बहुत hyperactive है. So that's about I saw up somewhere, that's about 13. Yes, that's about 13, 12.8 to be exact. That's about 13 breaths per minute, and that's that's a normal breathing range, by the way, right? I asked Isha to do some experiments for a higher breathing rate just to illustrate यार higher हो जाते हैं, and she did some experiments with 20 breaths per minute, Isha, or 30. Just when you said कि
I think that was a maximum of 20. वो भी बहुत मुश्किल था. It was very hard.
Really hard, right? So उसके बाद चक्कर आ जाते थे Isha को, right? With the 20 breaths.
Yes.
Right. So 12 or 13 breaths per minute. That's your guess of what the breathing rate would be. So this would be an extremely powerful tool once again in conclusion. Okay. So here are your tasks. I'm done. There are 5 tasks once again, which will hopefully take you not as long as lab 3. So we're going to get hopefully niche jate jayenge hum as far as the time taken to complete this task is concerned. Task 1 is just a completion of MATLAB on-ramp module. So there are 2 modules left. One of those modules, by the way, is has to do with Doppler effects. You're measuring the speed of stars using Fourier transform. वहाँ पे wavelength कह रहा है, लेकिन असल में wavelength is also Fourier transform. And that's a really, really interesting project that I found. Some people I know have already completed the entire MATLAB on-ramp module. So if you have done that, don't worry. You don't need to do this again. You just move on to task 2 and just share with us the certificate. Okay. One of the other actually important or interesting exercises that I wanted to say here, I had the TA do this, and we're facing some issues, which was if I play a tone of 15 kilohertz on my phone and I start moving this phone towards a microphone, what do you expect would happen? Daniel, आपका question I know, but since you've raised your hand, I take it that you want to answer this as well.
Yeah, it would observe greater frequency.
It would create a frequency shift, right? So the amplitude increase bhi karega, yes, that's true, but the frequency is going to increase as well, and that's called a Doppler shift. It's just like train, if it's moving towards you, the frequency increases, it moves away from you, the frequency decreases, and there's physics behind it. And the amount by which that frequency increases or decreases, you can tell the velocity or the speed of the train, right? And the interesting, maybe perhaps some of you can try it out. The interesting experiment you could try to do is, if you're playing a tone and moving the phone towards and away, can you detect a Doppler shift, right? And if you can detect a Doppler shift, this will allow you to have a way of doing gesture recognition. कि आप जो है अपनी उंगली ऐसा करते हैं या ऐसा करते हैं, ठीक है, चलो फोन के साथ ऐसे करते हैं या ऐसे करते हैं. Perhaps with that Doppler shift, you may be able to detect whether you're moving towards a microphone or away from the microphone, right? And in 2014, I believe, some of the undergraduate students who were working with me, they tried to do this relatively successfully. Okay. The second task is a frequency contact analysis. Sorry, this is a typo. This is content analysis of your own voice. You will try to see that आपकी frequency ranges 95% of the energy कहाँ से lie करती हैं. So if you have a dull voice, you would expect that to be lower. If you have a shriller voice, you would expect to be higher. And maybe we can have a competition to see which one of our students has the dullest. Dullest is probably not the right adjective. The content with the lowest frequency, right? And which one has a contest with the content with the highest frequency. We can have that competition on LMS as well on some groups. Okay. The third is low pass filtering that I've told you already. The fourth is frequency shifting, and the fifth is breathing rate estimation. So the last three tasks are more or less exactly what I've shown you in the slides as well. Okay. Now I'm going to stop here. What we're going to do next, of course, is you can leave this meeting if you wish. You will open up the lab handout, which is there on LMS, give it a read, which will point you to certain MATLAB functions that were provided you and gives you documentation for those MATLAB functions as well. How do you use them to compute the Fourier transform? Okay, so that's there on the handout as well as on LMS. I have also uploaded 2 tutorials on YouTube, and the links are there on the handout as well as on LMS. That perhaps may help you in doing those tasks as well. So यहाँ पे आपने low pass filtering implement करनी है. मैं task में I implement high pass filtering. So that should be extremely helpful for task 3 and perhaps for task 4 as well. Okay. Once again, we're going to break this down into groups. Each one of the TAs are going to man their own group sessions. If you have questions, specific questions, if problems, you can join those meetings and they're going to answer them, right? I am going to be in this meeting for another hour, right? So I will be able to take any questions that you have or concerns that you have, or perhaps the problems that you're facing in MATLAB. I can help you with those, but I may not be here after 5 p.m. Okay? So, khalas, that's it. Let's begin with the lab task. Any questions? Let me know. Daniel, you have your hand raised.
We excluded one of the modules, one of the tasks from module 10. Are we supposed to do that too?
Yes. So you